the acknowledgement and vast experience with our San Marcos National University community. This is the second conference in this history of our university, which is conducted in person and on digital platform online. The theme of this 5-day international conference is superconductivity and magnetism, which is relevant to Latin American technology and science. In the name of the organizing committee, we hope this conference will help our students expand their mental horizon. I would like to thank and acknowledge to Ciència, who give us the economical support to perform the conference, and the support team who has worked hard to make this conference a truly successful one. I request all the participants to take part in all the activities, and I wish everyone a successful and fruitful conference. Welcome to Lima. Welcome to San Marcos University. Thank you. And now, we have the words of Dr. Luis de los Santos Valladares.
Hola, hola. Hello, hello. Thank you very much, Juan Carlos Gonzalez. Welcome again to everybody to this conference. This is the second Latin American conference on superconductivity and magnetism. It is very nice to have here today to many researchers from Latin America and from Europe and Asia. We have prepared a very busy schedule for these days related with topics related with superconductivity, magnetism, theory, and experimental, based on physics, chemistry, material science, etc. The first Latin American conference, the first version of the conference, has been held here in Peru as well. And after we are returning to the second conference, the second version this year, because the pandemic has stopped some for a couple of years. I traveled to Colombia in 2018 and spoke with the Colombian researchers, collaborators there to organize the conference there. Unfortunately, the pandemic arrived and we tried to move again to Peru for 2020. The pandemic didn't finish and we have postponed it until this year. Well, fortunately, everything is sorted out, and thanks to the support of Concitec, Ciència, we are organizing this second version of the conference. The conference is hybrid, so it will be online and also here on site. For all of you that would like to give extra or some information or have some problem, don't hesitate to approach to us, to this, the organizing committee, and we are going to try to solve any issue that you have with your stay during your stay here in the conference. Well, I would like to take advantage today to have some small changes in the program, just tiny changes that, for example, you are wondering about when is the dinner. The conference dinner will be on Friday, 27th October. We are going to take advantage because it will be the closing ceremony as well. And also we are going to celebrate the birthday of Professor Ángel Bustamante Domínguez, which is on Saturday, this Saturday. And we are going to have a very big party for his birthday on Friday. Well, also as well, anybody, all of you that you would like to be connected by Wi-Fi, here on this, in this wall, you have the password of the Wi-Fi, it's free connection. Okay? to all of you that have not paid yet for the dinner or for the tour will be on Wednesday and will be, you can approach to the receptionist to pay by cash. It could be in US dollars or in euros or in soles equivalent. Well, thank you very much for you are here, all of you, and I hope that you enjoy your stay at the University of San Marcos and in Peru. Now, Juan Carlos Gonzalez, thank you very much.
Thank you, Dr. Luis de los Santos. And now we have the words of the Professor Ángel Bustamante, Chairman of the conference.
Ustedes comprenderán, acá estamos en una situación complicada, hay una huelga universitaria, entonces nuestros estudiantes y docentes un poco están citados para salir, digamos, a las calles y presionar al gobierno el asunto de los salarios. Bien, pero nuestra actividad académica es un compromiso con Ciència y con CITE. Por lo tanto, se tiene que iniciar el evento. Y yo estaba queriendo recordar siempre a aquellos colegas científicos que dieron vida y dan vida a la superconductividad y al magnetismo. Recuerden, hay que recordar que fue Camerlin Onnes, sobre todo cuando conocemos por la historia que él se dedicó 25 años de su vida para poder conseguir helio líquido. Entonces, ahí es donde perseverancia que debe haber de una carrera científica, que a veces decimos no sale, mejor por otro lado. Y Camerlin Onnes nos consigue helio. Entonces, el helio líquido casi en un volumen como de una taza de té o de café. Y entonces a partir de eso comienza a medir propiedades de los materiales a baja temperatura, entonces, y demuestra que hay en el mercurio una caída a cero de la resistencia. Y en el Physics Today dice que hay que él dijo una palabra de superconducción, y después ya los literatos o la gente que sabe más del asunto del inglés le pusieron superconductividad. Entonces hay que recordar a Camerlin Onnes. Eso abrió entonces una carrera de la física dentro de la materia condensada. Superconductividad y magnetismo pertenecen a la línea de la materia condensada que está ahí en el rol de actividades que tiene la Sociedad Americana de Física. Entonces somos de la condensed matter, como se dice. Después, posteriormente, entonces tenemos a F. London, o primero a Maynard y Orsfeld, que logran descubrir el famoso efecto Maynard, que consiste en que este material expulsa campos magnéticos, lógicamente hasta cierto valor, porque de alguna manera, como dijo Abrikosov, ¿no es cierto?, pueden ingresar campos magnéticos cuantizados que los llaman vórtices, ¿no? Y también está London, que ya conecta entonces las propiedades electrodinámicas de los superconductores y complementan las ecuaciones de Maxwell. Y él propone entonces que hay dos fluidos, electrones normales y superelectrones. Lo dice en el Physics Today, donde sale la historia de la superconductividad. En 1950 viene Ginzburg y Landau y desarrollan una teoría fenomenológica para explicar las propiedades termodinámicas de la transición del estado normal al estado superconductor. Pasan los años y en 1957 ya se va armando una teoría microscópica para entender la física de estos nuevos superconductores. Y aparecen Barden, Cooper y Schiffer, que le dan entonces conocidos como BSC, donde ellos también ganan el premio Nobel en el año de 1972. Pero, haciendo un poquito de historia, antes de ellos habría otro científico, Froelich, que escribe, ¿no?, y da una primera forma de hamiltoniano para entender, ¿no es cierto?, la parte teórica de este fenómeno. Después viene en el año 62 Josephson, que usando la teoría BSC y demuestra que dos placas superconductoras interactúan, digamos, aisladas por un aislante, y encuentra entonces que la corriente también se traslada del primero al segundo y se nombra ahora el efecto Josephson. Y vamos a ver que ese efecto Josephson, de alguna manera, viene a ser parte ahora también de un nuevo dispositivo que está ahorita saliendo a flote, que es los qubits para la computación cuántica. Él recibe el premio Nobel de Física en el año 1973. Después, en el año 1973, el físico norteamericano Matías descubre un compuesto a base de niobio y germanio. Fíjense, su estudio hace que la temperatura crítica ya no es a nivel de helio, 5K, sino 23K, 4 veces más. En 1986, los alemanes Müller y Ambenners demuestran que usando tierras raras, y lo vemos ahí que usó lantano, bario, cobre y oxígeno, él alcanzó una temperatura de 30K. Y en el año 87, dado que ya vieron que la tierra rara era importante, vienen los físicos americanos Paul Chu y Max Wen-Wu y descubren el compuesto a base de la tierra rara, itrio, bario, cobre, oxígeno, y escala la temperatura a 93K. Es decir, ya ahí comienza la era de lo que ahora llamamos los superconductores de alta temperatura, 93K. Y en 1988 se encuentra un material superconductor a 110K, es decir, siempre buscando de romper la barrera, levantando la temperatura crítica. ¿Con qué elementos? Con bismuto, calcio, estroncio, cobre y oxígeno. Siempre ahí el cobre y el oxígeno, ¿no? Y da entonces a una temperatura crítica también de 125K para un compuesto con talio. Lógicamente, bueno, talio, calcio, bario, cobre, oxígeno, pero talio es pues extremadamente peligroso trabajar con talio. En el año 93 también se descubre mercurio, bario, calcio, cobre, oxígeno, y con una temperatura crítica de 135K. Y así siguen, tratándose de ver, subiendo más que la temperatura crítica sea más próxima al medio ambiente. En el 2014, Física reporta que Michael Eremex y sus colaboradores del Instituto Max Planck para Química descubren que el compuesto sulfuro de hidrógeno H2S, que fue preparado a alta presión como 100 gigapascal, usando un anvil de diamante, tuvo una temperatura de 60 K. Y la sorpresa fue de que cuando ellos elevan la presión a 150 gigapascal, la temperatura crítica que debía de descender se disparó, dice, a 190 K. Eso está reportado en el Physics Today de julio del 2016. Pero en todo ese proceso de elevar las temperaturas, poco se ha hecho o no está todavía culminado la teoría científica para estos nuevos superconductores. Pero eso no deja de que estos materiales comiencen a trabajar. ¿En qué sentido? En el sentido de que ahora usted tiene imanes, ¿no es cierto?, de altos campos magnéticos. Y ahí hay empresas que ahora, o los chinos, ¿no?, tienen los trenes levitados magnéticamente que le llaman los maglev. También tienen ustedes el dispositivo interesante que se llama el SQUID, que permite capturar o sensar campos magnéticos pequeños, como por ejemplo el campo magnético del cerebro. Hay una foto que se ha mostrado en la conferencia donde la resonancia del mapeo del campo magnético del cerebro usando los SQUID modernos, la resolución crece mucho mejor que digamos, los equipos antiguos. Y así se puede ver que hay muchas aplicaciones desde el punto de vista macroscópico y también microscópico. Bueno, pero todo eso uno no lo hace solo. Siempre tiene que generar, como docente universitario, la mayoría somos, se tiene que generar grupo de trabajo o atraer a los estudiantes para colaborar. Recordando, aquí en la universidad se tiene que dividir en grupos de investigación. Entonces, yo me recordé de una palabra en un libro donde llamaban pues Functional Materials. Dije, bueno, vamos a generar el grupo de investigación llamado materiales funcionales, que es lo que tenemos acá al frente en nuestro laboratorio. Y oh, sorpresa, ahí está también varios de nuestros alumnos. Y en otro, y ahí está también Luis, profesores, que han hecho su tesis usando presión química, formando una estructura de itrio, estroncio, bario, que no era fácil de formar porque requería presión. Entonces lo primero que se comienza es haciendo presión química con boratos, sulfatos, fosfatos. Hay salió todo un review de esa forma. Pero lógicamente ahora las evidencias, ahora está pues de moda y como estamos en interrogación, si lo que han hecho los coreanos es valedero o no es valedero, porque hay todo un problema de que no se puede replicar. Y si usted descubre algo, un material que tiene su temperatura, por decir 250 K, alguien lo tiene que replicar y no estar escondiendo, digamos así, la información. Y hay todo un problema con Nacho que publicó, ¿no?, digamos, el ensayo o las muestras de los coreanos, me parece. Y bueno, yo con eso lo que quiero mostrarles es que nosotros en esta universidad, digamos, somos los únicos, por decir, en el Perú, que estamos relacionados con esta área del conocimiento, ¿no? De superconductividad y magnetismo. Y espero entonces que las conferencias les sean gratas para ustedes, que usen también en un momento determinado, prueben también la gastronomía peruana, y con eso entonces yo les doy las bienvenidas, y cualquier cosita pueden ustedes acercarse a Luis, a mi persona, Melvin, y el otro colaborador, a Víctor. Muchas gracias.
Many thanks, Professor Ángel Bustamante. And now, following our schedule, we have the speech of Doctora Ana Palau from Instituto de Ciencias Materiales de Barcelona, con el speech on Engineering High Temperature Superconductor for Efficient Functional Device. Doctora Ana Palau, please.
Hello, morning everyone. I would just like to thank very much Juan Carlos and also the organizers to give me the opportunity to participate to this meeting, which I think it's really interesting, and I'm very, very happy to be here. And I'd like to show you a bit the work that we do in Barcelona regarding superconducting materials, especially high-TC superconductors. And in the talk, I will just give you different examples of different things that we, in a very general way, different examples of different systems that we explore in order to give you a brief introduction of all our work and see if we can find any synergies with what you do here. As you know, superconducting materials are materials that can be very useful to go through different challenges in our world. For example, in the environment and energy field, we need to treat the energy in a sustainable way, and superconductors with, for example, coated conductors and other materials and systems can be used to improve the efficiency in the energy storage or transmission. In the case of information and communication technologies, as you know, in this new world that we have a lot of information and Internet of Things, big data that we need to compute, and we need to manage and storage a lot of data, and these also have to be in a way that it's sustainable for our environment. And here also, superconductivity may be efficient to design devices that can be used in this field. And in the case of quality of life, also superconducting materials are well used in MRI, for example, or for ultra-sensitive squid sensors. So superconductors, as you see here, are materials that may be used in many different fields, and in our group, what we aim is to try to go in this direction, to try to explore different systems and materials that may be used in order to improve or to give information and communication systems that may be more efficient than the ones that we are using up to now. as I said, sustainability is something that is very important in this field of the information and communication technologies, and big data centers needs a lot of power in order to be maintained, and also supercomputers that has been used in order to manage big data also use a lot of energy to work. And in all this field, sustainability and high efficiency, it's very important in order to reduce the impact on these systems, on this field in the data management and storage. And superconductors with proper unique properties like quantum coherence and intrinsic energy efficiency, because they can conduct electrons without any heat, any losses, are materials that can be intrinsically more efficient than the materials that we use as normal conductors. And there are many different systems that have been explored using superconducting materials to perform filters or rectifiers, antennas with large, very good performances, also squids or sensors or detectors that also use these technologies. And in the case of computation, quantum qubits can be performed with superconductors, and also we have the flux quantum electronics. All these systems, all these different approaches have been and are widely explored using low temperature superconductors, which are conventional superconductors with a critical temperature below 30 K. But in our group, we are trying to work with high TC superconductors. In these materials, we could use the property that with high TC superconductors, we can use nitrogen to refrigerate the system, so reduce the power requirement for the system. And also, there are several properties that high TC superconductors may introduce in order to improve the efficiency and the functionality of the devices. For example, these materials are strongly correlated to oxides with peculiar properties. They have high TC, high JC, and large HC2. They can work with higher fields and higher currents. And also they have a proper 2D structure and asymmetric properties that can also be tuned in order to modulate the performance of the materials. However, the use of high TC superconductors to perform and to design, fabricate devices, it's quite difficult because they have properties that give pose problems in order to work with these materials. For example, they have extremely small coherent length, which means that they are very sensible to nano defects. Any defect in the system can affect very much the properties of the system. Also, the properties strongly depend on the content of the oxygen in the structure. This is the structure of YBCO, and we have oxygens in the structure that controls a lot the properties of the material. So the oxygen compound in this compound is a key issue for the properties. And also the structure of the material may be very well ordered because we have these copper oxygen planes where we have the superconductivity going on, and in these planes may be very well grown, so the ground has to be very well epitaxially grown on especially substrates, which is not simple sometimes. The different approaches that one can use in order to fabricate nanoscale or microscale devices with high TC, we have different techniques: focus ion beam, electron beam, or a combination of different techniques, high resolution lithography techniques that can be used in order to nanostructurate the system and fabricate the devices. But in all the cases, what we need is to be very careful because we can damage the sample during the processes of the lithography. Also, lift-off techniques may be complex since we need these special substrates, and sometimes it's not simple. And also one has to think that in these materials we have a lot of defects, and as I said, the presence of defects may affect a lot the properties of the material. So all of these things need to be in mind when one wants to work with high TC materials. And what we have done is explore different approaches in order to fabricate these devices. One first approach is to use high TC materials in contact with or combined with ferromagnetic materials in order to try to see if we can fabricate or try to think spintronic devices. We also can work with the geometry of the material in order to play with the vortices. The vortices are the quantum flux lines that appears inside of the material when we apply magnetic field, and the motion of these quantum flux lines can also be used in order to fabricate devices. And finally, we can make profit of the fact that these materials are strongly correlated oxides to play with the oxygen in the material and play with the current density in what's called motronic devices. In the first case, as you know, the possibility to play with non-trivial magnetic states, which could be vortices, fermions, monopoles, all these systems may be very interesting in different communication technologies, for example, in order to build memories or to transport information. And the main bottleneck playing with these materials is the fact that very stable systems need to be worked with large currents, for example, and the bottleneck in these systems is the balance between the thermal stability of the system and the operation power that one needs to operate with these systems. Superconductivity may be key in this problem, because in a superconductor we can pass current through the system and stabilize magnetic fields without any need of energy. And with this idea, one can think on the possibility, for example, this is a theoretical work where they define the possibility to work with the vortices to move or to imprint different textures in a magnetic material. And in fact, this has been explored experimentally, in this case, by using low temperature superconductors. They were able, in these works here, they were able to imprint.
Con este duermo. Pero si quieres te lo doy ya, si duermo con otro. Mira, voy a escribir. ¿Qué? Ah. ¿Las plantas de esta? Sí.
Por eso que defendió.
Okay, so in this work here, they were able to imprint vortex avalanches in different magnetic systems, and the avalanches generated in the superconductor could be seen when removing the magnetic field in the superconductor, and could be imprinted in the ferromagnet. With this idea, we also try to work in systems combining high-temperature superconductors with ferromagnets. And in this work here, what we did is to nanostructure different dots of a superconductor, YVC superconductor, and the shape of the dot could completely control the imprinted structures in the ferromagnet. For example, in this square dot here, we have domains pointing tail to tail or head to head, or here we can able to imprint this kind of textures. Also in these circular dots we could imprint monopolar like fields where all the spins could go in the center or out of the center of the material. So many different structures could be imprinted just because, or using the non-homogeneous magnetic field of the, which is trapped inside the superconductor. And In these systems, for example, here I show a square dot and the evolution of the remnant magnetic field that is imprinted in the ferromagnet by using the magnetic field trapped inside the dots. And what we see is that many different structures, many different non-trivial structures could be imprinted and could be stabilized at zero applied field just by using the trapped magnetic field in the superconductor. And these different structures could be used in order to build different memory levels. Also, in a more complicated structure, in this case, what we use is a ferromagnet, which was a 3D ferromagnet, in this case, rod, which was grown with a particular texture in the ferro, like a nanorod. And here, for example, what we did is in a YVCO layer, we fabricated different dots in the layer, and inside of the dots, we put several nanorods. And these nanorods has a particular 3D magnetic structure, vortices inside the nanorods, and we try to move or to control the magnetization of the nanorods with the superconductor. And this would be a micromagnetic simulation of what would happen in one rod. What we have is the stabilization of two vortices states, one with the axis perpendicular and the other one with the axis parallel to the rod. And when these rods are embedded inside of the superconductor, these are the magnetic imaging of this rod, the magnetic domains of the rod, measured when the rod was magnetized above Tc at room temperature and with zero field cool below Tc. And in all these structures, we more or less reproduce what we have here theoretically with the stabilization of these two vortex states. When we go below Tc, we see a contrast which is different, and if we go below Tc with a field cool, which means that we have trapped magnetic field in the superconductor, we're able to change the structure of this rod with two vortices to a pure vortex state. So we are able to control the magnetic structure in a configuration of 3D nanostructure, which can also be thought as a possibility to work with different magnetic states. And how to read these magnetic states? What we perform is a very simple proof of concept of a way of reading different states that can be stabilized with the superconductor. And in this case, by combining a superconducting strip with a ferromagnet strip, which were insulated through an insulating layer, by applying magnetic field, we could change the magnetic contrast of this magnetic structure, and we could read the different states in the magnetic structure by measuring the magnetoresistance. And this would be the result, the resistance as a function of the applied magnetic field. If we do all the tests above Tc, we don't see any change in the magnetoresistance because we don't introduce any change in the magnetic structure of the magnetic system. But when we do the experiments above Tc, below Tc, sorry, what we have is penetration of flux inside the superconductor, and we have several minor loops that are totally reflected in the magnetoresistance of the ferromagnet, and so many different ferromagnetic states can be stabilized at zero applied field. This would be at remanence when we perform different loops in the superconducting system. So we could think that on these systems, on these hybrid systems, a way to build different memory states in the ferromagnet, which can be stabilized at zero applied field just with the supercurrents of the superconductor, which wouldn't be dissipative at all. Okay, so now I change to, this is another example of hybrid systems that we have explored. And it's a project that we have just started now, and it's a project based on the fact that we can combine a material, thinking on the metamaterial word, which is trying to nanostructure the material in a way that you can obtain properties from the material just coming from the nanostructuration of the material and combination of different materials structured in a different way. By using this metamaterial idea, what we have performed is to play with the possibility to combine the antagonic properties of the superconductor and ferromagnet. And since a superconductor is a material that tries to repel magnetic fields, and a ferromagnet is a material that tries to keep all the magnetic field inside, if we combine these properties in a clever structure, what we can do is to play with the magnetic field and play with the properties of this magnetic field. And in particular, what we have explored is these flower-shaped structures when we can combine superconductors and ferromagnets, or just work with a ferromagnet, which is also possible because you just don't need the superconductor. The superconductor just improves the properties of the material. And what you create here is a concentrator of the magnetic field, which could be used to enhance the properties of a magnetic system. The magnetic field inside of this structure would be amplified by this fact, and this can be optimized. And in the experimental system, what we have is this flower-like structure, which has been performed of permalloy, in this case without the superconductor. And what we put here inside is the detector, which is a rod, ferromagnetic dot. And by creating vortices in this ferromagnetic dot, what you could do is to track the magnetic field inside this structure. Since the position of the central of this vortex it's linear with the magnetic field, by tracking this position, one can see if what's happening inside of this concentrator. And these are the experimental results. What we have done is to image, by using magnetoptics, the position of this central vortex core. And by keeping and tracking the position of this core and tracking the position as a function of the applied field, we see that without the concentrator, we have a displacement which is much lower than in these data points here where we use the concentrator. So by playing with the concentrator geometry, we are able to improve the magnetic field inside the core of this concentrator, and we see that this is completely isotropic and can be used in order to provide an enhancement of the performance of different detectors or functional devices like energy harvesters, for example, that can be placed inside of these structures. Now, I go to the other structures, the other systems, in which we use the geometry of the material in order to try to play with the vortices in the system. And in this case, we are exploring superconducting nanowires. The use of nanowires, since the size of a nanowire have a size which is of the order of the parameters, key parameters of a superconductor, the coherent length and the penetration depth, several funny things can happen inside a superconducting nanowire, like different reentrants of the superconductivity, which were explored in nanowires, for example, in this work here, in nanowires based on low TC superconductor. We explored kind of these systems in high TC, and what we perform is nanowires in YVCO. This is quite tricky because in a YVCO we need to have, to mill the system and to perform these nanowires by trying to not lose any oxygen or not having any implantation of gallium or something in the material that could damage the properties of the material. We optimize the milling conditions in the system in order to perform and fabricate these nanowires, which could be narrower as 50 nanometers. And by exploring the properties of the nanowires, in this graph here I showed the JC as a function of the thickness of the nanowire, the width of the nanowire, sorry, and we see that the critical current density can be enhanced up to very, very high fields by narrowing the nanowire, and we approach the pairing current in the system, which means that in this case, we have the maximum critical current density that the system can support without any losses for the vortex motion. And we have seen that here, in fact, what we have is a region where the nanowire doesn't have any vortex inside. And here I plot the value of He2, which has been calculated from the position where we have the first vortex inside of the system. And we see that this Hc2 scales with the width of the nanowire, and we have in the very, very narrow nanowires up to 1 Tesla without any flux penetration, which means that we can have a region, a very wide region of magnetic field where we can play with the system applying currents without flux penetration. And this could be a candidate, for example, to fabricate noise-sensitive devices where the penetration of the vortex introduces a lot of losses. Also, these nanowires can be used in the other regime when we have vortex penetration, because when we have the penetration of the vortices in the nanowire, we have kind of the vortices penetrates in the nanowire in a very sharp way, and what we have is very sharp voltage transition at the place where we have the penetration of the nanowire. And this transition can be controlled with the width of the nanowire, and can be also the position where we have this current, where we have the switch of the voltage transition, can be tuned with the temperature and the nanowire width, which with these systems can be used, for example, for single photon detectors, where this sharp transition could be used to detect the presence of a photon which could hit the system. And finally, I would just finish with the last approach that we are exploring in our systems, which is the modulation of the properties of the system by modulating the oxygen content in the system. And in this case, what we use is the property that we have in a superconducting high TC material. In particular, we work with YBCO, by the fact of these materials are non-conventional superconductors, are oxides which are strongly correlated oxides. This means that these strongly correlated oxides, which are not just high TC superconductor, but also manganites or other oxides that have special properties, these correlated oxides have a very complex interaction between the charge, the spin, orbital, and lattice, and all these different degrees of freedom in the material may give a very, very complex phase diagram. In the case of the YBCO or high TC, we have a complex phase diagram where we have the superconducting state below a dome, which is controlled by the critical temperature, and here the doping of the material would change a lot the properties of the material, going from an antiferromagnetic state to the normal state, and in between a lot of different quantum phases that can be used for different functional applications. And the transition between one state to the other state can be induced by different properties, by different inputs, for example, the temperature, the strain, the field, and by changing from one position to the other, we change a lot the electronic and the spin orders in the material, so we change a lot the properties of the material. And in particular in YBCO, what we have is the possibility to go in this, to change this axis, the whole concentration, by changing the oxygen in the system. This is the TEM image of a YBCO layer, and we have here the structure of the YBCO, and the structure of YBCO is 7 minus delta. This delta is the amount of oxygen that we have in the system. By changing the amount of oxygen, we change the amount of carriers in the copper plane, and we change the axis of the whole concentration here. So by changing the oxygen in the system, we can go from the insulating to the superconducting state, and we can change completely the properties of the electronic properties of the system. In this graph here, I show the resistance versus temperature of a single layer, which has been switched to different states, means that we have gone through this axis by applying voltage pulses. And for example, we see here that starting from the superconducting state, this one, which will have a TC, we change to different insulating states by applying different voltage pulses, which means that we reduce the concentration of the oxygen in the system. And this can be induced in a reversible way. We can go from one system from one level to the other in a reversible way. And here, I show here the properties of this system, which these properties has also been found in different strongly correlated oxides and is what is called resistive switching, which means that you can change the resistance of the system by applying voltage pulses. And in this graph here, I show here the resistance versus voltage, and you see here that, for example, in this loop here, the red one, by applying a voltage pulse, we change the system to a very high resistance state, and then by applying a negative voltage, we come back to the low resistance state, which means that we have two different levels and also intermediate levels that can be modulated by applying impulses in the material. And by changing the structure of the gate would be the electrode where we apply the voltage pulse, we can change the level of the low resistance state and the high resistance state, which scales with the area of the device. And this means that we have a consistent transition below the gate, and we have a consistent change of the oxygen doping inside the gate. And in this case, for example, these systems could be used in order to design memristors for neuromorphic devices. Because in a neuromorphic device, what we need to emulate is the brain. It has been demonstrated that the computation of the brain is very efficient in a power point of view, depending on the processes that you want to compute. And in a brain, what one has to emulate is the neurons and also the connections between the neurons. And the connections between the neurons is what's called synaptic plasticity, have some kind of memory that may be storage in this connection, and this can be storage in these kind of systems because the resistance can be modulated depending on the amount of oxygen that we introduce in the system. And this is something that it's non-volatile and it stays for a long time and can be switched from one state to the other by applying voltage pulses. And with these kind of systems, different behaviors that may be modulated for a synapses can be obtained. So at room temperature, these kind of systems playing with the oxygen could work like a neuromorphic neuron, and the neuromorphic connection between neurons. Moreover, the possibility to move and to control the oxygen in the system can also be explored and be used at low temperature and see if we are able to change the superconductivity in the system. And in this experiment, what we did is to change or to move the oxygen in the system by applying a current through the system. And with this current, we induce motion of the oxygen in the system, which would change the oxygen content and the resistance. And in this video here, what we can see is the change in the brightness of the image when we change the oxygen content, when we apply voltage that drift the oxygen vacancies in this direction and then come back and drift the oxygen vacancies to the other direction. So we are able to control the amount of oxygen that we have in the system by applying a current in the system by moving the oxygen ions, and change the contrast of the image because we change the resistance of the system. And by exploring different situations, one can tune the critical temperature of the system because since we changed the oxygen inside of the system, what we change is the critical current density. Starting from the pristine state, we can introduce or reduce the oxygen and move and drive the system to the insulating state, and by applying current in one direction. And in order to track the change that we introduce in the oxygen, what we use is the micro-Raman experiments. With the Raman experiment, using the Raman spectra, one can track the delta value of the oxygen content in the system by exploring the vibration of this oxygen here. And by doing so, what we have done is try to explore after different electromigration runs, which would be the oxygen in our system in different positions of the track. And what we see is that in the pristine state, we have the proper oxygen content in the system, the delta that corresponds to a well-oxygenated state. And when we go to different electromigration runs, we observe that in the central part of the system, where we have the large amount of electric field, what we have here a concentration of oxygen vacancies. What we see is here that this oxygen position shifts, and we have this dip here in the amount of oxygen that is enlarged when we introduce a higher electromigration run. So with this, we can track and have a quantitative analysis of the delta and thus the doping of the system. And we can build this kind of graphs, TC as a function of the electromigration run, and the current density also as a function of the electromigration run. And we can do this at different regions of the track. We have different track widths. Here at the edges, we have the width of the track a little bit wider, and then thinner track in the middle. And what we see is that moving the oxygen in this direction, what we see is that the oxygen vacancies in this direction, here that we don't introduce any oxygen vacancies. We have the TC that we expected and we had at the beginning. And in this part of the track, we have a reduction of the TC, and in the central part of the track, we have a deeper reduction of the TC. And the same is observed when we observe the carrier density. The carrier density at this part of the track, the blue one, is increased a little bit, because what we do is to move the oxygens in this direction, so we increase a little bit the doping, and here we introduce a lot of oxygen vacancies, so in this case the current density decreased. And if we put all this data together in a TC versus carrier density phase graph, this is the squares are data that have been taken from bulk system that has been oxygenated in different states, and the stars are different points that have been obtained by the electromigration runs. And what we can observe here is that we can go through the phase through different oxygen states in the system. And what's interesting here is that this can be done in a simple sample. We don't need to, in this work here, they use many different samples oxygenated at different states. And in our case, by starting with a well-oxygenated sample, we are able to go to different states by just applying the current in the system. And here is just this graph in the phase diagram, and what we can see here is that we can go from the superconducting metallic state to the insulating antiferromagnetic state by just playing with the oxygen content in the system, which is quite interesting to explore the different phase states or phase the complex phase diagram that we have in a high TC superconductor in a simple sample. And finally, what we have explored is what happens with the critical current density in the system when we change the oxygen. And here I show JC versus the critical current, the magnetic field, as samples that have been, this would be the pristine state, and these would be different samples that were shifted to the high resistance state. And what we see is that we reduce the critical current density, and the critical current density versus field has different behavior depending on the oxygen content. Here by showing JC as a function of the switching procedure, we see that if the switching introduces low changes in JC, this is reversible. It can be changed and come back to the initial state. But when we change the JC in a large amount, like in this case, we, for example, we go from this system to the red one. When we want to come back to the pristine state, we are not able to recover completely the JC. We can just go to these two intermediate states because there are several irreversible changes that we introduce in the material if we do very large, we introduce a lot of oxygen vacancies in the system. And this has been explored by TEM, and what we observe is that comparing a pristine sample with a sample that has been switched to a very large high resistance state, what we see is that at the top part of the system, what we have is a large amount of stacking faults, which are defects that are introduced in the copper oxygen plates. Is an extra copper oxygen plane in the system, which can be here observed as a dark contrast. And the presence of these stacking faults, what we induce is an extra kind of defects in the system that cannot be released when we come back to try to come back to the initial state. So if we introduce vacancies in a way that we do not generate these stacking faults, we have a reversible state that can be switched and switch back to the initial state. When we introduce this large amount of defects, then we can change a lot the properties of the material, but we don't change we cannot come back to the initial state. And finally, to show that this effect can be introduced at nanoscale by, instead of using large contact, if we use a small contact, like here, for example, we use an AFM, which is a current AFM tip. By applying current in this tip, which is nanometric, we can introduce different resistance states. This would be the resistance of the system. This would be low resistance state, and the bright ones, high resistance state. And this, from low to high resistance state, can be reversibly introduced at nanoscale by using these current pulses using the AFM. Also, it can be generated instead of using current, using heat. And in this case, this is a work that we have started to recently to try to modulate the oxygen. Here we see the contrast of one image that has been irradiated with a laser, and with the heat that we generate with the laser, we are able to introduce oxygen vacancies in the system, also modulate the TC by changing but the heat. I leave you here final summary of the different approaches that I have shown. Just showing different structures combining ferromagnets and superconductors, playing with the nanowire width, trying to work with the vortices in the material, and also trying to play with the oxygen content in the material in a reversible or non-reversible way to change the properties of the superconducting system. Thank you.
Hey, thanks, Dr. Ana Palau. It's good to see you again. No, I hope you enjoy Lima and hope not to stay here in Lima for another opportunity. And now we are open for questions. No, or yes.
Thank you very much for your nice talk, Professor Ana. I have a question regarding the phase diagram. You have shown the last one as a function of the whole concentration, where you have overlaps on experimental data. Yeah. obtained by electron migration. Do you have an idea about what is the gene of the discrete have with one data at the left of the exactly?
This
exactly
one?
that
Yeah.
one.
Yeah, I think that this is just to show you that more. Thank you. So this is just a way to see that you can modulate the TC and also the carrier density, and it more or less follows this trend. But exactly, this is carrier density, and in this case, this is oxygen doping. And oxygen doping is related to the carrier density, but it's not the carrier density itself. So we have not been evaluated directly the carrier density, and we can have big changes in here. But it's just to show that we can follow this trend, and this needs to be more analyzed if you want to exactly know exactly where you are in the system.
Thank you very much for your interesting talk. I have two related questions concerning your experiments with electromigration. Can you please go a few slides behind? No, further?
Yeah.
No. Back.
Back?
Yes.
But electromigration?
Yes.
Here?
No, more.
More back or more? Because this starts
You
here.
showed multi-terminal structure with
This one. No.
earlier.
This one?
No. Yes, this one.
Okay.
Thank you.
Okay.
So, question number one. Suppose you created pattern showed on the right image, red and blue one.
Red and blue, okay.
The two dots, one with depleted concentration,
Yeah.
one with enhanced concentration. So, question number one. If you anneal the structure to higher temperatures, can you establish the precene concentration? And question number two. If you reverse the polarity of the battery, can you reverse blue and red dots?
The thing is, we have done this experiment in using current and using voltage. The electromigration would be using current, and also we can introduce frequencies using current. The effect is very strong, but it's not reversible. So when we apply in one direction, we deoxygenate this part, and we oxygenate this part, and it's not reversible. And if we measure shorting 1 and 4, we see that we lose oxygen in this electromigration experiment, which is introducing a lot of defects and introducing a lot of heat. If we do the experiment with voltage at lower oxygen content, we are able to completely move the oxygen from one way to the other without any change, any losses to the atmosphere, any losses, so just move the vacancies inside of the system. And in this case, when we shorted 1 and 4, we obtain no changes, because what the change of oxygen going to one position to the other is the same. So the resistance, the amount of oxygen is just moving to one way to the other, and it's reversible.
Thank you.
Epitaxy. I'll just repeat the question just in case people didn't hear. Thank you for your talk, very interesting. You said that you can make the superconducting alloys with epitaxy. Is that well controlled? Can you control the oxygen levels and the crystal quality?
Yeah. This is the key, and they has to be grown in a very special conditions. We have optimized the system, and we grow the the layers with PLD. And what we do is using special substrates, which are LAO or STO. We control very well the heating of the substrate and also the pressure, which is very important, and the temperature of the heating ramps. And we are able to grow the system with a very good oxygen content, which give high critical current densities. If this is not well controlled, then the system is not superconducting.
Is another question? No? Yes. Oh.
Thank you for the interesting talk. We have very short question and very quick question there. And you presented that you have put doped with columnar size for the vortices and fixing the pinning vortices. And in that system, you presented the electrical measurements. I am wondering if you measured that with the magnetic properties, such as AC or DC susceptibility.
No.
What do you expect in the dynamic of vortices in that case?
Yeah, we didn't explore. We just measure critical current density as a transport critical current density. And what we see is that the presence of these rods introduce an extra field in the system, or as field that it's the coming from the rod and reverse to the superconducting system. And what we see is that we have a shift in the position of the maximum JC due to the presence of the rods. But we have not evaluated the AC measurements.
Okay, great. Thank you.
Well, it's maybe another question, or maybe the last question, no, to end this talk. Well, please give the chair and applause for Dr. Ana Palau from Material Science Institute of Barcelona. No, many thanks indeed. Yes. You can disconnect. So following our schedule, we have a break, and start at 11, 11 a.m. Thanks indeed.